Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the math series we will be going into our very own calculus. No, the one and only calculus. Okay, never mind, that was weird. So today's topic is differentiation, and since it is a huge topic in its own right, and even schools separated into differentiation techniques and differentiation application, I'm gonna do the same too. So part 1 will be about differentiation techniques, and part 2 will be about what you do with the differentiation, as well as application questions in general, and how to tackle them. Okay, so yes, this is part 1. So I'm going to talk about the different techniques and how to do differentiation in general. And as with all things that's talk about differentiation, I think the best way to start is to talk about why differentiation works. I'm not gonna go through the details of the history and the whole battle between Newton and Leibniz and all that stuff, because that's not. There's enough information on that out there, but the main reason how differentiation works is what we call first principles of differentiation, and it kind of goes a bit like this. If you draw a line, like your graph, and you want to differentiate that line. So differentiation is ultimately finding the value of the gradient of the curve at a specific point. So how do you start? You first start with a very, very rough version of your gradient. So you just choose 2 points and you draw a line that connects both of them. And obviously that's not the gradient. So in order to make it more and more the gradient, you keep decreasing the distance between those 2 points until you reach a point where the 2 points are pretty much the same point. And that's when you get the differentiation, like the gradient of the line at that particular point. So what does this mean in symbolic terms of, like, how do you represent that in writing? Basically you define these 2 points as x and x plus delta x. So the first, like the point before is x and the point after is x plus delta x, and you want to make delta x as small as possible. And likewise the ensuing y will have y and then y plus a delta y, or the better way to represent it is, if you're using fx instead of y, you have fx and fx plus delta x in the sense. So in order to get a gradient, what you do, you put delta y over delta x, right? So in this case, since we do not know what delta y is, you would instead represent it with fx plus delta x minus fx over x plus delta x minus x, which would simplify to f of x plus delta x minus fx over delta x. I hope you got that. I would have probably written it down. So that is your d or dx of fx at this particular point, or at any point, because you're being very generic here, you're not specifying the point yet. So if you want to, so you now need to simplify this thing, and it usually works based on what example you're using. Like if you're using x squared, your fx will just be fx plus delta x will be like x squared plus 2x delta x plus delta x squared. You know what I mean? Yeah, and minus x squared. So you only will have terms which have delta x in them, and therefore you can numerator and denominator, and you will get 2x plus delta x and plus delta x. Yes, so what's the final step of this entire thing? Well, bringing delta x to 0, because that's the point, right? You're not supposed to have 2 points, you're only supposed to have 1 point. So if you make delta x tends towards 0, you will get your answer as 2x, and that is the differentiation of x squared. How brilliant. And this is what you memorize as, well, super generic formulas that you're supposed to remember and do your exam with. So I hope actually understanding how it works makes you appreciate it a lot better than you do right now. And let's move on to the actual stuff that you need to know for your exam. Yeah. So I'm gonna start with what are the sorry about that. I'm going to start with the differentiation of various functions like x squared and all that, and then I will go into the rules, and then I'll go into the graphical interpretation of that. I think that's a better order according to me, because I started with first principle, so I should probably go in that direction. Okay, so as we all know, x squared, if you differentiate it, you get 2x. And likewise for x to the power of n, if you differentiate it, you will get n, x to the power of n minus 1. And yeah, that's about it. There's nothing crazy about that. I think you all know how to do that. Yeah. So let's move on to something more complicated, or like something different, I guess. So you have sine x, like the trigonometric function. So sine x will give you cosine x, and cosine x will give you sine x, negative sine x. And you can either prove this using your first principles, or you can just draw a graph of sine x and then see how the gradient of the graph changes. Because if you think about it, the sine x graph is positive, and then the gradient becomes 0, and then becomes negative gradient. And you know that the cosine x graph is positive until 90 degrees or pi over 2, and it becomes negative after that. And that's why your sine x graph, when you differentiate it, you'll get cosine x. And likewise, you can prove that cosine x, the differentiation of cosine x is, if you differentiate cosine x, you'll get negative sine x. Yeah, I'm just gonna continue here. I don't think you want the proof for everything, so yeah, I'm just telling you how to prove it. If you want to prove it and just make sure that it definitely is this and it's not something else, in a sense, yeah. Okay, let's continue. So you have sine x becomes cosine x, then cosine x becomes negative sine x. And what about tangent x? Well, if you want to prove it in a way, you can use the quotient rule, which I will talk about in more detail. So maybe you use it during that time. But d of dx of tangent x is secant square x, and for secant x you will get tangent x secant x. And if you have your 1 over sine, 1 over cosine, which is arcs. Yeah. Oh yeah, secant and cosecant. Oh yeah, I just told what secant is. Okay, so cosecant would be okay, let's start with cotangent. Cotangent x will give you negative cosecant square x, and then cosecant x will give you negative cosecant x cotangent x. Yeah. Yeah, that's pretty much that. I do remember that there's a bunch of derivatives written in your M26, so just take note of which one they are and memorize the rest of them, I guess. And then afterwards you will have your e to the power of x, which is forever e to the power of x, no matter how many times you derive it. Yeah. And then you have your ln x, which will become 1 over x. And yeah, there isn't anything else that you would be able that you cannot find in your M26 or anything. Yeah, it should be fine. Okay, so yeah, I think let's move on. So we've covered some basic terms that you should probably know how to differentiate. And I know there's some other things that you may need to differentiate or something, like the 1 over square root of 1 plus x squared or something like that. Wait. Actually, you can technically just differentiate that. That one is more for the integration part. That's more important. So yeah, let's move on, and you'll now cover the different techniques that you use to differentiate stuff that's a little bit more complicated than this. Okay, so the very first one that you know is when I don't remember the names of everything, so I hope you understand what I'm talking about. The chain rule, I think so. I think it's a chain rule. And for the chain rule, if let's say you have f of you have f of x, and if you change the x to something like 2x or x squared or something, so how do you differentiate that? Well, you first differentiate fx and you times it by the differentiation of the function that's inside the fx. So if it's like f of 2x, you will get 2 times f prime 2x. But of course, when you write the f prime, you must write the 2x, don't write x, because that doesn't make sense. So for example, if you have sine of 2x, you'll write 2 sine 2x. Okay, cool. And likewise, if you have e of x squared, you will write 2x times e to the power of x squared. Cool. I think we all get where this is going. You all understand what is going on here. Okay, good. And if you're using ln x and you have things that you can cancel out, go ahead and cancel it out, because it should work. I think it will still work by right, because there is two simple, like the similar factors on both sides of the fraction. So yeah, just cancel it out. Like for example, if you have ln of x squared, which is actually equal to 2 times ln x. That's the reason why it works. Right? If you think about it, if you differentiate 2 ln x, you get 2 over x. If you differentiate ln of x squared, you will get 2x over x squared, which will become 2 over x. So it's the same thing. There is no issue. Yeah, it's usually with ln when you do that. Yeah, there isn't anything else that I need to worry about, right? Yeah. Sorry, my nose is blocked a bit. Yeah, so the next rule is the product rule. And the product rule is when you have to differentiate uv, for example, like u and v are both functions of x. So how do you differentiate this? The rule of course says that you first differentiate u and you times it by v, and you plus it with the differentiation of v times u. And the reason why this works, I honestly do not remember the proof right now. Actually, you can just use first principles to prove it. It should work. I remember that it works with first principles, so just use first principles and you understand why it works. Yeah. I mean, if you really want me to prove everything with first principles, I could do it, but that's gonna make this even longer than it already is, and it's more fun if you do it yourself, so just do it yourself. Yeah. Yeah, so basically that's how it works. And for the quotient rule, likewise, you don't need to use first principles this time. If you've already proved the product rule, you can use that to prove the quotient rule, which is if you have u over v and you want to differentiate that, you had to start with v, because if you think about it, if you're differentiating 1 over x, the negative comes from the power, not from the actual x. And wait, what am I saying? Okay, I mean, sorry. If you differentiate 1 over x, you'll get negative 1 over x squared, right? So likewise, if you differentiate something that is over v, like you would get a negative when you're differentiating the v, if you think about it, because 1 over x, when you differentiate x, you're basically getting 1, so you don't have any new power on top. I mean, that's why it's still 1. If you want to differentiate 1 over x squared, it becomes negative 2 over x cubed, if you think about it that way. And likewise, when you differentiate 1 over v, the whatever derivative of v will be negative on top, because it's a fraction and the denominator will have a negative power. And that is why when you write your quotient rule, you will start with du over dx times v, which is positive, minus dv over dx times u, because that's the negative part, so that's why you minus it instead of plusing it, and over v squared. I think that was pretty obvious. That's pretty simple to understand. And if you still need a rigorous proof, you can use your product rule, or if you're being extra adventurous, you can use first principles. It will be quite annoying to do this with first principles because of the denominator, but you can still do it with first principles. It should work by right. I think I've done it before, but if I show it to you, I'm gonna waste 2 minutes, so let's move on. Okay, so is there any other rule? I doubt it. I thought there were 4 different rules. Oh, okay, the first rule was the power rule, which I already covered, so I guess that's pretty simple. Right, yeah, the power rule, what we covered earlier, the x squared becomes 2x and so on and so forth. So if you apply that to other functions like sine x, for example, if you have sine squared x, you would do the same thing. You would do a power rule and then you would do a chain rule. So the power rule will be like what 2 sine x, and the chain rule would mean that sine x will become cosine x. So you get 2 sine x cosine x, which would equal to sine 2x, and therefore that's why the differentiation of sine square x is actually sine 2x. Yeah, brilliant. Okay, so let's move on. Yeah, those are the 4 rules of differentiation. I do know there's a lot of other rules that you need to take note of, like the sign of the derivative and all that stuff. But I think you guys should know that by now, so I'm not gonna go through that. It's too much of time. Like, it's not really worth going through. Okay, so next thing we'll go through is the should I go through implicit? Okay, so we'll go through implicit differentiation, and that would be that is pretty interesting actually, because if you have both x and y in the same thing, in the same line, your function, then you find it hard to differentiate it, right? So there are 2 ways of going about it. You either isolate the y, like you make it a subject, y equals to something something x, or if that is super hard to do without making a really complicated function, you can just do implicit differentiation. So how implicit differentiation works is, of course, you differentiate this with reference to x, and that is important because you're not differentiating it with reference to y, you're differentiating it with reference to x, and that's the important part. So you differentiate each and every term with reference to x. So for example, y, we do not know what dy over dx is, so we just write it as dy over dx. Yeah, that's how you differentiate y. And if y is in a function, use your chain rule. Like for example, if it's y squared, you can use your chain rule to make it 2y dy over dx. So likewise, you can apply it for whatever function of y that you see there. And for the x, you do it as usual. You just, just do your differentiation as usual. So let's use your chain rule, your product rule, your power rule, and your quotient rule, and just do all your differentiation implicitly on the terms. And once you're done with that, you can actually isolate dy over dx. Of course, you may get y on the other side of the equation, but if you do know what y is, like if you have a value for y for a particular value of x, you can actually find out dy over dx without any issue. Or if you know I don't know, you can figure out a way of doing that. And in questions they will ask you to usually find out, they'll usually make you continue doing it, and they'll use it in Maclaurin's series sometimes. So we'll cover that in the next episode, so do look forward to that. I guess. Yeah, you can just keep continuing and then do a second derivative, third derivative, fourth derivative, and so on and so forth. It's pretty useful, it's a pretty useful tool, this implicit differentiation. And the other thing that they were talking about is parametric. And you know what parametric is, right? Yeah. Okay, so for parametric differentiation, it is like your polar function. You use a parameter in your polar functions like t or theta, and likewise you use another variable in this differentiation to find the answer to differentiation. And of course I somehow learned to do this in secondary school because we had a chance to do advanced maths, which was just JC maths, so yeah, okay. But actually it was mostly a lot of differentiation and integration to it, so yeah, it was fun. I think that's why I like calculus because it's straightforward. It's like if you know what you're doing, you know what you're doing. It's about as simple as that. Okay, so never mind. Okay, so for the parametric differentiation, I don't think they really test you this that much, but if they do, then just take note of it. It's basically you have for example, you have something like what should I use? Can have something like you can have something like ln of sine x. Wait, no, that's actually okay, right? Yes, that's not the sorry, that's not that's not what they're supposed to do here. Okay, let me think. Okay, never mind. Let's just say you have a function which is hard to differentiate, and or it could be something like 1 ln of something or sine x or something like that. Some weird trigo function that you can't really differentiate properly. And usually the answer is the one which gives you the 1 over square root of x squared plus like 1 minus x squared or something like that. Yeah, that kind of thing. I think you can see that in your M26, so it's not really an issue. But still, if you get a function that you can't really differentiate, and it's not even like y and x in the same place, but it's just a hard function to differentiate, you can do this thing. Like for example, if your function involves a trigonometric function, usually that's the case. You can make, for example, you have sine x in the function, right? And you can use your if you're differentiating, actually they use this in integration, sorry. Never mind. But if you're differentiating something, you can substitute the function for another variable. Like for example, you can make your sine x equals to u or something like that, and then you can differentiate u on its own. You don't need to think about sine x yet. So when you're differentiating u, you write it as du over dx. And after you do that, then you can differentiate. Since you know the differentiation of u, you can just put that in and you'll get your final answer without it sounding too complicated for you. So usually in this case, when they give you the question, it seems a bit dumb because otherwise it'll be, if they give you an overly complicated question, you may not even know what to substitute for, or even if they tell you what to substitute for, you don't really know what you're doing. Yeah. So I'll write it down a little bit for about 10 to 20 seconds to show you how it works, like what you're supposed to do when you get a question, but I'm not going to really solve any actual question. I'll just show you how to convert, how to write, how the notation should go about. Okay, so, yeah. Sorry. Okay, so hopefully I finished writing it by now. Oh man, it's already 20 something minutes. That's why I wanted to split this into 2 parts. Right, so so the next thing I'm gonna talk about is the I don't think there's anything else. Okay, so I go to the graphical part of it now, because I think that's the easiest thing that's the next thing I should be talking about. Okay, so for the graphical interpretation of the derivative of something, since I've just told you at the very beginning of this that finding the derivative of something is like trying to find the gradient of the graph at the particular point x in that sense. And yeah, that's pretty much it. The derivative graph is just a gradient. You know what I mean? Like you think about it, it's like your physics. You have your displacement, your velocity, your acceleration. The velocity is basically just your derivative graph of your displacement, and likewise the acceleration graph is the derivative graph of your velocity. Yeah, so I think you know how this works now. Of course, if you don't take physics, then the other way of looking at it is, if your gradient, the gradient of this graph, if you were to measure the gradient at each point and plot it into another graph, that is a derivative graph. and you can keep continuing it for your second and your third derivative, and so on and so forth. Okay, so for your graphical interpretation, of course, if you know if your derivative, if your f prime x is greater than 0, then your gradient is positive, which means it'll be, you know what I mean, positive, pointing in that direction. And if it's equals to 0, it'll be straight. Basically, it's like a horizontal line. And usually in a curve, it'll just look like one single point at the maximum point of the curve, or the minimum point of the curve, which I will cover more of in the second part. And if it's lesser than 0, it will be a negative gradient. And of course, the next important thing to take note of is the second derivative. I'll cover more on the whole test in the second part, but I'll just tell you what it means if your second derivative is positive or negative. So if your second derivative is positive, it means that your first derivative is increasing. That's the simplest way I can put it. Your first derivative is increasing. And if your second derivative is less than 0, it means that your first derivative is decreasing. But your first derivative can be positive or negative. It's just that it's increasing or it's decreasing at that point. Okay, so if you were to convert fx to f prime x, I think this is the last thing I'll cover today. I'll cover the rest. Sorry, in this part, I'll cover the rest in the next part, because it's already gonna become 27 minutes, and yeah, it's annoyingly long if I tell everything at one go. Yeah, and I can't speak. Oh great. Okay, so to make your fx graph into a derivative graph, the simplest is actually pretty simple. It's even better than the one or fx graph, because this thing is just looking at the gradient. If your gradient is positive, then your graph should be positive at the point. If your gradient is 0, then your graph should be cutting the axis at the point, or touching it, depending on how the graph looks. And if your gradient is negative, then your graph is negative. It's as simple as that. There's nothing crazy about it. And for the asymptotes, it depends on what your graph looks like. If your graph looks like something that is, if you have an x squared graph, and the top part is really high up, and it would have been going to, negative infinity, then of course your line 2x will be starting from, negative somewhere, and going up to positive somewhere, in that sense. But if your graph is something like, let's say if you have like a x cubed graph, okay, actually for the asymptote ones will only be, usually only comes when your original graph has an asymptote. So let's say your graph has an vertical asymptote and is going from infinity towards 0. And in your gradients, since it's going from infinity to 0 and it's in the negative region, so I'm imagining like a negative gradient, your derivative graph will also be going from negative infinity, because it's a very high, almost vertical kind of a gradient, until 0 in a sense. So if let's say if it has a minimum point of 0, this will also have a line, a graph that cuts the axis at 0, 0. And yeah, in a way, that's how you draw your fx to f prime x kind of a graph. And likewise, you can reverse it for your integration. You can just reverse it, and the same thing should work. You do it the opposite way, and you can convert an fx graph into a f prime x graph into a fx graph. Okay, cool. So I hope you understood everything I told in this part, and if you're looking forward to the next part, do go and click it. And with that, I would like to say thank you, and looking forward to talking to you in the next part. Yeah. Yeah, bye.